So section 5.6 is about concavity. We're still justifying conclusions about the behavior of a function based on the behavior of its derivatives, but this time we're going to look at the second derivative of our function. So the definition first of concavity, a function is concave up like a cup on an interval where the second derivative is greater than 0. So you have that cup shape on this graph for part of the graph. And if I took, this is a graph of f, just to emphasize, so the f looks like a cup, f double prime would be above the x-axis. F is concave down like a frown when the second derivative is less than 0 or negative. So f looks like a frown, f double prime would be below the x-axis. We talked about linearization. We were talking a little bit during that time about whether a function is over or underestimated by using linearization. And the thing that determines that is the concavity of the function. Because if you have a concave down function, your tangent lines are going to be above the graph. And if it's concave up, the tangent lines would be below the graph because the slope is increasing on those concave up sections of the graph. This is a phone game that I used to play a long time ago. I don't know if you've ever played it, but it's called Tiny Wings. And the goal of the game is you're this bird, big bird, but really tiny wings. And you can't really fly, but you can kind of leap off of hills. And this game got me really good at identifying inflection points because you get the best lift on these hills as your little tiny bird if you tap it exactly when the bird is at the inflection point. The inflection point is the place on the graph where the concavity changes. Without the tool of a derivative, it's very hard to see the inflection point with your eyes. Just by taking a look at the graph, it's hard to see where the inflection points happen. So the way you find an inflection point is you look for a sign change on f double prime. So you're looking for that sign change on f double prime. That could happen if f double prime is equal to 0. It could also happen if f double prime is undefined. The sign change is what's necessary. So when you are justifying an inflection point, make sure you mention the sign change. You can say f double prime is equal to 0, but that's not enough to prove an inflection point occurred. If all you know is that f double prime is equal to 0, then what you know is that you have a possible inflection point. If you don't know whether there's a sign change, then you don't know whether you have an inflection point. So we're going to do an example. Here's our function. We want to figure out where the inflection points are. So we'll take the first derivative, because this is chapter 5, and let's always start by taking a derivative. This is a product. It's also a chain. So the derivative of x is 1, e to the 2x left alone, and then x left alone, and the derivative of e to the 2x is going to force me to use the chain because it's not just e to the x. I'm going to rewrite that a little bit. And then I'm going to take a second derivative. E to the 2x is going to involve the chain rule, so e to the 2x times 2, and then product rule again. So 2 times e to the 2x left alone plus 2x left alone times e to the 2x times 2 because of the chain rule. Now I'm going to add some like terms. So I have 4e to the 2x plus 4x e to the 2x. Now I want to look for sign change on the second derivative. Sign change could happen if the second derivative is undefined, but this particular second derivative doesn't have any asymptotes or discontinuities, so this second derivative is defined everywhere. Or it could happen when the second derivative is equal to 0. So I'm going to find the zeros of that second derivative. And in order to do that, I will factor. Each term has a 4 and an e to the 2x. So that's my GCF. So then I'd have 1 plus x. Now I look for zeros. Um, this factor is never going to equal 0 because e to the x is always positive. And this factor would equal 0 if x is equal to -1. So if I'm going to look at a number line chart again, but this time I'm looking at a chart for f double prime. -1 is the only point, and I'm going to look if I'm smaller than -1, then this value would be positive because e to the x is always positive, and this value would be negative. So I have a negative value on f double prime for less than -1, and for larger than 1, I have a positive value for f double prime. So if I want to justify an inflection point, first of all, point means ordered pair. So what is f of -1? So I have an ordered pair. That would be -1 times e to the -2. So if I want to justify it, the inflection points are -1, comma, -1 over e squared, because f double prime changes sign at x equals -1. That's a justification for an inflection point. You're welcome to mention that f double prime is equal to 0, but the sign change is what really matters for your justification. Here's a graph of that, so you can see how hard it is to eyeball where an inflection point happens. It happens at -1, and it changes from concave down like a frown to concave up like a cup, but it's not as obvious as just taking a look at it and saying, oh, for sure, that's concave down. It's really pretty flat. So it's important to look at your second derivative. All right, for this example, I am looking for where is my function concave up. I'm looking for what intervals it's concave up. It would be possible to multiply this function out, but it actually would make your life much harder. So let's not do that. Let's look at it as, let's look at it as chain rule and product rule instead. So it's a product of x minus 1. So the derivative of that is 1. Oops, I did that wrong, didn't I? I need to leave that one alone. So I'm going to do derivative of x minus 1 times x plus 3 cubed plus x minus 1 left alone times 3 squared times 1. All right, so that's my first derivative. I'm going to maybe rewrite that a little bit. Now I'm going to take a second derivative. This is going to be chain rule. And then product rule again. So the derivative is 3. And then 3x minus 3 left alone. And then chain again. Now, as I look at f double prime, I see that I have 3 terms because there are 3 plus signs, and each of those terms has an x plus 3 in it. So I'm going to factor that x plus 3 out. Actually, before I do that, I'm going to add these two like terms together. I missed that part. So these are like terms. So let's go ahead and add those together. Oops, not in yellow because that's hard to see. So I have 6. All right, so I'm looking for where that second derivative is equal to 0. I can see that the second derivative is never going to be undefined. And I see that both of these two terms have an x plus 3 factor in them. So I'm going to factor x plus 3 out. If I take an x plus 3, if I divide this by x plus 3, I have 6 times x plus 3 plus, if I divide this term by x plus 3, I have 6x minus 6. So then I have x plus 3 times 6x plus 18 plus 6x minus 6. So that would be x plus 3 times 12x plus 12. All right, so I have inflection points or possible inflection points at x equals negative 3 and x equals negative 1. So if I look at my sign chart for the second derivative, negative 3, negative 1. If I am way smaller than negative 3, my second derivative, this part would be negative, and so would this part. So this would be a positive value. If I'm between negative 3 and negative 1, this value would be positive. This value would be negative. And so then that last interval is positive. This function is concave up on the intervals from negative infinity to negative 3. You can include the negative 3 if you want to. You don't have to. And from negative 1 to infinity. So this is the interval where that function is concave up. If I look at the graph, I can see that we have concavity, concave up until negative 3. Now it's concave down until negative 1, and then it's concave up again. So we can see that in the graph. This last example, we're going to go through this one in class because it's a calculator example. But if you want to try it on your own, this would be take the second derivative and figure out on your graphing calculator on this interval, so you have to change your window, figure out when your second derivative is positive or negative, and that's going to be your intervals of concave up and concave down. So again, this section was all about what does the second derivative tell us about our function, and it is all about the concavity of that function. Thank you so much.